Oh, little Flo, I love you so, especially in your nightie. When the moonlight flits across your tits, oh Jesus Christ almighty.
Greetings, the Astro 30 here, and today we've got another electronics video for you. Today I'm going to be assembling this 1969 power supply unit for those Class A modules. I just noticed I've forgotten to add a component to my schematic, but that's just going across the negative and positive rails respectively. Anyhow, I have reverse engineered this to a schematic. Let's take a look at that. So here is the reverse engineered schematic. We're using a center tapped transformer, and that'll become evident in a minute. It's going through an MBR 20200 CTG, which is a 20 amp 200 volt Schottky barrier diode or barrier rectifier, which is forming what is known as a full wave rectifier, not a full wave bridge rectifier, but a full wave rectifier. And there is a difference, and I will go through that in just a minute. We've got two filter caps of 22,000 microfarad each. There's also a 100 nanofarad across here as well, but I've forgotten to draw that in. And that gives us two VDD or plus voltage outputs. The ground just comes over here off the center tap, which forms our negative rail for the single-ended amplifier. And it says in the circuit description that it does actually include a speaker protector in inverted commas, but it's not actually the way you think. What they mean by that is a turn on, turn off de-thump circuit. So we're basically providing a small turn on delay before allowing the speakers to be connected to the amplifiers, and an instant turn off. So that's comprised around this circuit. Now, starting up here, we've just got a standard button bridge rectifier here, which is a 2W10. Comes off of one side of the AC transformer secondary, and also the center tap to form the other side of the full wave bridge rectifier. And then, of course, we've got a positive here and negative here. Now, at no point is this negative referenced to this ground point over here. Just keep that in mind. Got a small filter capacitor of 2200 microfarad. That's going through a small dropping resistor of 10 ohm, 1 watt device. And then we're going through this circuit here. R2 and C4, which is a 300k and a 220 microfarad respectively, is our RC delay. So our RC time constant, and that will give us a turn on delay of roughly 3 seconds, because it will slowly ramp the voltage up as this charges for this transistor Q1 here to turn on at 0.6 of a volt. This resistor R3, which is a 68k, is basically a bleed resistor for this capacitor. Once the power is removed, then this capacitor will discharge through this resistor, making this capacitor discharge a lot quicker. So if the power was interrupted momentarily, say it was turned off and then a second later it was turned back on, well, hopefully in that time this resistor has bled off enough charge that you get some form of delay before it switches the speakers back on, so you don't get the thump through the speakers. Now, this is the transistor driver stage, Q1 and Q2. I've marked them as 2N3904s. They're not. They're actually double S's 8080 transistors, which I have no idea what they are, but they have a HFE of around about 293, and they're connected in Darlington configuration. So the emitter is at the negative rail of the circuit, and the collectors that are joined together are now connected through the relay coil to the positive rail. And we've got just a flyback diode here, D1, which is an 1N4001. Now what is interesting about this circuit is mainly we've got two 10 ohm resistors of 1 watt value each connected on the normally closed position of each side of this relay, going to the actual circuit earth, which is up here in the power supply, but not this negative rail that this is referenced to. That means that when this relay is off in its normally closed position, these 10 ohm resistors are going to be across the output of the amplifiers, each channel respectively, because one's the left, one's the right. And I'm not 100% sure why they have done that, why you'd want to load the amplifier with 10 ohm especially, when it's not actually driving any speaker. Now, if in some unfortunate instance the amplifier was working hard whilst driving across those 10 ohm resistors, these are only 1 watt devices. So if you were pushing the full 15 watts out before this relay actually engaged and connected the speakers, well, yeah, just think of the amount of current going through these resistors. They're going to burn out pretty quick. So I'm not really sure why they've preloaded the outputs, but they're Chinese. What else can I say? So that's the circuit. It's pretty basic. Just imagine there's a 100 nanofarad capacitor in here. I'll have to go through before I finish uploading this video, because I'm going to make this available for you to get a copy of, and I'll fix up my little errors I've got here. It's only one really. But now let's go through how this part is actually working. We've got a transformer, right? The AC is on that side, so that's 240 volt. Now we'll need to explain the difference between a half wave and a full wave bridge rectifier. So we'll ignore the fact a filter capacitor for this demonstration. So if we just put one diode on one of the ends of the winding here of the secondary, we'll assume that this is a 24 volt transformer. Okay. Now if we have a single diode here, this is known as a half wave rectifier, because we're only rectifying one half of the waveform. So our expected output on an oscilloscope screen is going to be that. So we're only going to have a hump each half cycle. Now, with a full wave rectifier, if we add another diode in, so we're now, when the AC signal is going in the negative direction, this diode is conducting, but now we've got a slight little problem, because we can no longer use the output in the same configuration. So we need a transformer with a center tap. So on this side we've got 12 volt, on this side we've got 12 volt, and at this center point is our load. So this is the positive, this is going to be the negative. And if we measure without a filter capacitor across here now, our waveform on our oscilloscope screen is now going to look more like that. So we're actually rectifying each half of the waveform and giving ourselves all these humps with no gaps in between. However, a full wave rectifier requires a center tap transformer. It will not work without one. Now there is one issue with this. Now assuming 24 volt center tap transformer, so 12 volt 012, that means our expected DC voltage here is going to be 16.9 volt. That's it. Not anywhere near like 32 volt which you would kind of expect if you were to go 24 times 1.414 would equal around about 33 volt. Because this negative is now referenced to the center tap, that means it's only ever going to be half potential. So that actually will be 12 times 1.414, which equals 16.9 volt. And that's all we're going to ever get. So that is the disadvantage to a full wave rectifier. The advantage is you're rectifying both halves of the AC waveform, but the disadvantage is you're only getting half the voltage out of the transformer. So how do we rectify this issue? Well, you could just use a full wave bridge rectifier, because that will give you a virtual negative, if you like. So this is a full wave bridge. Negative is formed off of that side, positive off that. So that's positive, that's negative. Waveform output is still going to be the same without a filter capacitor, and that's joined there, of course. And you will actually get the full voltage out of the transformer, so it will be 24 times 1.414, which is roughly 33 volt. So we'd have 33 volt across positive and negative. And if we've got a center tap, we can actually ground that and have a 0 volt rail and make this bipolar. Those are the differences between the three types of rectifiers that are used. Why are they using a full wave rectifier? I'm not too entirely sure. They could have just used a full wave bridge rectifier and achieved the same thing. But I think they wanted to use a center tap transformer because, like a 36 volt center tap is, or 38 volt center tap is probably more common. Remember, we need 25 volt here. So a 12 volt, 12 volt transformer is not going to work because we're only going to have 16.9 volt. We need something more like an 18 volt transformer, and after rectification that is going to be 25.7 volt, which is close to the 24 volt we need. So I'm going to prove how that full wave rectifier works, because I've given you the theoretical explanation, but we're not going to just take my word for it. What I'm going to do is I'm going to solder on all the connections and this Schottky barrier diode without the filter caps installed, and we're going to have a look at the output on a scope for a start, and we're also going to measure what its voltage is. But that means I'm going to need an 18018 transformer. Aha! I'm going to borrow the transformer out of the test amp because that's an 18018, and use that for the testing of this, because this has a 24 volt relay, so there needs to be at least 24 to 25 volts on this side of the circuit. So again, a 12012 or 24 volt center tapped transformer is not going to work. Okay, so let me just put that part on, and it's just a TO220 device and a heatsink that's soldered to the board. Both are supplied. Doesn't look like there's any isolation component for it, but you'll need to put some heatsink compound on it. I'll probably just use a transfer washer. And yeah, we'll get testing. Right, so I've put the diode on the heatsink with one of these self-adhesive TO220 isolation washers plus a bushing. So I'm isolating the heatsink from pin 2, well this is actually called pin 4, but the center pin anyway, because that's our positive output, and they've got these pads really close to the inside of the heatsink, so I don't really want it to short on anything. So we've got one three-way connector, actually we've got three of them. So I reckon all these three ways go on this side, because it's 1, 2, 3, 1, 2, 3, 1, 2, 3, yep, plus two ways on this side. So we would join these together like so before putting them in the board. They should fit like that. Yes, they do. A little bit tight. There we go. So that's one side in, and do the same on the other side. I know this is kind of counterintuitive to actually assembling all the smaller components first, but I am going to be using my tool to do that, so it's not going to be a great big deal. So just make sure all those are flush. I can turn him over, and I'm going to use some leftover solder from some other kits here. Get rid of that first, just to you know, use it. Might as well, it's there. Let's start by soldering these terminal headers in. Okay, so that's the terminals all soldered in. Now I can install a rectifier. And I'm going to start by soldering the location pins in first at the heatsink. These are just blind holes, they go nowhere. They're not earthed or anything. Which would be a bad day if it was, because if you just screwed the diode straight to the heatsink and these were earthed, yeah, well, let's just say the circuit wouldn't work correctly. So that's those pins soldered in. So now I can solder the actual main device. Okay, so that's that, and I can trim off my excess leads here. So that's one piece of the puzzle. Again, as I already said, I'm assembling it backwards, but that's only so I can present to you what I am talking about. So what I might do is I might hook up the leads I need for the plus VDD lines and ground, plus the AC inputs, and because they're over here, these are just the speaker terminals. Yeah, and put some standoffs on it so it's not scratching the crap out of the desk, which may also be counterproductive because I'm probably going to have to take them back off. But anyway, let's get set up for the next part of the test. Right, with everything all set up, I've got the AC wires from the transformer out the test amp, secondaries going into each AC connection. The ground point or center tap is going to where the center taps are actually joined on the transformer in this case. I had to unsolder a wire from one of these leads because that's how I made it. This project probably will never work again, but I'm not really particularly fussed at this point in time. Got the multimeter set on the output. It's currently saying we've got 0.6 of a volt there at the moment. Plug is plugged in, so all I have to do is just turn the power switch on. And would you look at that? Unsmoothed, we're getting 19 volt. So if we were to use a 24 volt center tap, that would be a lot lower. 19 volt is still respectable. I'm just doing a heat test on that diode. It's not really doing anything, but that's unsmoothed DC. The voltage would be a lot higher when the filter caps are in. So let's actually have a look on an oscilloscope screen now what that output looks like. Okay, I got the DSO hooked up across the DC output. We're at 5 volts per division, AC coupled. So I will now turn this on. Well, it's really hard to see that waveform, so if I drop my voltage per division down, you can actually see that that's what the output is. It's like an AC waveform, and it reckons it's a V peak to peak of 2 volt, but it's trying to measure AC. So that's what rectified, unfiltered DC output looks like. So we can turn that off, And now I can think about actually assembling the circuitry. However, I can actually hear you all asking through the screen, hey Astro, what is the actual DC output voltage with the filter caps installed? Well, just for shits and giggles, let's install the filter caps. Again, counterintuitive to how you're supposed to assemble it. And actually test again what the DC output is on the meter. I was just double checking these aluminium capacitors. They are not used, they're not pulled, they're brand new. Yeah, 22,000 microfarad at 35 volt. So, I'm going to install, without having to unwire all my secondaries here, I'm going to try to, yeah, that works, try to solder the necessary leads here without disconnecting anything. I'll get one pin started. See, that was much easier to solder to than what was in that other amplifier. Much easier. That's why brand new capacitors help. Okay, that's soldered. Now do the other two pins. Not much solder left on that one. Right, there we go, that's soldered in. I'll turn it back over. God, that looks huge. Okay, so I'll connect the multimeter back up again and we'll have a look at the output voltage. Okay, I've got that set up. It's plugged back into the wall. Am I nervous about powering it up for the first time? Well, yes. Just before I do that, I'll make sure I double check that the negative's pointing the right way. Yes, it is on those capacitors. Nothing worse than having them backwards and it going bang. So let's turn it on. And now we can see a big difference. We now have around 27 volts DC at the plus minus output. So before we had 19 volt, I believe it was. Now we've got 27. Now these caps are rated at 35 volt. So you wouldn't want to go any higher than an 18 volt transformer. Or I should say an 18-0-18. That's all I've got for now. Probably find a 15-0-15 would work better. So if we had 15 volt AC, multiplied that by 1.414, we'd be looking at closer to 21. But don't forget that this circuit is unloaded. It's not connected up to the amplifiers, it's not actually got any other circuitry on there loading it down. So, alright, time to disconnect all this and finish assembly up on the rest of the circuit and see if we can get it to work. That's another thing to watch. I've just powered off the transformer and those caps are holding a charge for a very long time. As we can see, it's falling off very slowly because there's no bleed resistance there at all. So that's going to take a long time to discharge. If I could find a resistor like a 10k or close enough, 1 watt, that I could stick across those VCC terminals to effectively short it out, then yeah, I could get rid of the voltage. Okay, I couldn't find a 1 watt device, but I found a half watt device, 10k, so this might go up in smoke. I can smell that resistor already, but it is bleeding off charge fairly quickly. What I'll do is sit there
save myself sitting there holding it all damn day is I'll just connect the resistor up across the output and with some jumper cables so it can bleed off like that. So I might have to let it sit a few minutes. Really don't want to start soldering to the circuit board with that amount of voltage hanging around on those caps, because one slip of the soldering iron and yeah, there's sparks galore. But that's bleeding off relatively fast now. And a short time later, all the components are installed but the relay, because I want to test what the voltage is across the relay coil before I install it. They did supply me with a 24 volt DC Omron relay, which is nice. Now, two things. I haven't installed the 10k dropper resistor for the LED. Well, one, because I don't actually need it at this point in time. And two, the LED is not supplied in the kit. It is missing. That's wonderful. And also the 1N4001 diode was also missing, which is kind of handy, and that's kind of important because that's our back EMF diode for the relay coil, so we don't kill the transistors with back EMF when the relay turns off. So I just stuck a 1N4004 in there. Doesn't matter, you can use a 1N4007. It doesn't matter. So now I'm just going to hook this back up to the transformer, and I'm going to measure the voltage across this relay coil and then install the relay. Okay, the transformer's hooked back up. It's plugged into the wall. I'm going to turn it on. Hopefully nothing will go bang, but these are rated at 35 volt each as well, so it should be fine. And we're only going across one half of the winding of the transformer, so from the center tap to one side of the AC winding, so we're still only getting 27 volt there roughly. So let's turn him on and stand back. Alright, nothing exploded immediately, so I'll just turn him off temporarily. Okay, I've got my multimeter across the relay. It's slowly discharging, of course. We've got 25 volt, so connecting the relay in there, that's going to drop down to probably 23. So I know that that's working. Okay, so I need to solder in that relay, but remember our main filters is going to still have 26 volt DC on it, so that's going to be, can be considered lethal if you come into contact with it, but for now I'm just going to carefully solder the relay in. Okay, that's done now, and that was an extremely tight fit because the pitch between the holes there is probably a little off. So let's turn the switch back on. 3 seconds and it comes in. Nice. Turn it off. It's not exactly instant off, it's probably a delay of about 200 milliseconds there, but let's see what happens when we turn it back on again. Still 3 seconds. So even with the power supply interrupted momentarily for like 3 seconds, that 68k resistor is enough to discharge the 220 microfarad capacitor that's in the RC delay there, enough to still allow a delay when turning the relay on, so it doesn't suddenly instantly come back on, reconnecting your speakers all of a sudden and producing an annoying pop. So what now, I hear you ask? Well, just going to monitor the temperature of that. It's fairly cool still. The next thing would be to, well, I really need to assemble that other module, so I've got two of them. Thing is, this is only a 52 V, I can't remember offhand what VA rating that is. It should be written somewhere on the transformer. We've got 1.4 amp per winding, so this transformer is slightly underrated
for this Class A project, I'd need at least 160 VA transformer with 3.2 roughly amps of current per winding. So powering it anywhere close to full power on the amplifiers would be probably disastrous for the transformer, just saying. So anyway, what I might do is take a short break, make the modifications I need to my schematic, and yeah, I'll move on to something in a minute. Okay, and I've got the second Class A module all assembled. I didn't take any video of it. What's the point? Just like I didn't take much video of assembling the power supply. Again, what's the point? It's pretty simple. Now I've got it hooked up to test point 1, which is just the positive of the output capacitor here. That's connected across my DVM between there and ground on the volt scale, because the first thing we've got to do is adjust that pot there on the right for half the supply voltage. And I've currently got my benchtop power supply with the load off set to around what that power supply is going to be outputting, which is 26 volts. So I'm going to turn the load on and see if everything goes bang. No, but we've got 700 odd milliamp current draw. The LED is on. This heatsink is underrated. I used 2 new transistors as well because, well, one of these refurbished ones has got a dent in the can. So the other one's alright, but yeah, it looks crappy, so I didn't bother using it. So I don't know what I did with the other 2 either, but anyway, now let's do a quick heat check on these transistors. Getting slightly warm. Anyway, we are roughly at 13.5 volt, which is roughly where half point is, but I'm just going to drop that down to something a little bit more respectable. I think, no, that's the right pot. I thought I was adjusting the wrong pot. We are now around half the supply voltage. Now we're about 26.1, so we're about 26.03, 13.03. That's close enough. Now to adjust that pot on the left to get a current draw. Now someone said when I previously made that other amplifier module that the current should be set a lot higher than where I set it. I think I set it at 800 milliamps. It should be more closer to 1.2 because it's supposed to operate between 0.8 and 1.8 amps quiescent current respectively. So I'm going to adjust that second potentiometer, watching the current meter on the supply, until we get a quiescent current of approximately 1.2 amps. Around about there. And those transistors are starting to get hot. That's the whole idea of Class A. Those transistors at idle will get hot. Now, the other thing is, now I've adjusted the current, my half voltage point has dropped as well. So I might back the quiescent current off back to 1 amp, just because I can. That should be a little bit more respectable. 1.2, maybe a little bit too high. I mean, it's really up to you when you actually do the sound test. If you want higher quiescent current, it may give you deeper bass, it may not. But I reckon 1 amp or thereabouts would be perfect for this module. And that heatsink is getting warm. Transistor's warmer than the heatsink in the bracket. But yeah, it's probably not going to get any higher than that until it's working, but those transistors are pretty hot. So
My halfway point voltage is at 12.9, so I might just tweak that, because the current and the voltage are actually in concert with each other. So as soon as you increase the halfway point voltage, the current will start to drop down again. So it's really much of a balancing act there. Yep. So I want to find out how hot those transistors are actually getting. So I need my temperature probe in my multimeter so I can find out. Yeah, about 52, 54 degrees Celsius, maybe 55. I'd say around about 60. It's too hot to touch with my thumb, but it's not going to exceed the SOA curve of the transistor, which is around 160 degrees Celsius at the die. So I know that even though the transistors are fairly hot to touch, but that's again class A for you, and it's sinking that heat into that small heat sink quite significantly. So I probably wouldn't want to run it for too long because the heatsink is inadequate. But all's well so far, so now I need to do the preliminary tests of hooking it up to an oscope and signal gen and see what the output's like. Okay, I got everything hooked up, got the function generator at 1 kilohertz, 1 volt. Just want to make sure nothing's going to short on anything. That would be a very bad day indeed. The output of the amplifier is connected across an 8 ohm dummy load, the oscilloscope across it, and now we'll power it up and hopefully we have an output. Which we do, but I've got my seconds per division wrong for a start. There we go. And yeah, we've got an output. We're currently pushing 12.7 volt peak to peak. The sine wave's nice and clean. I have kind of forgotten what the maximum amplitude input is before clipping, so I've got to take it up to that. So I'll turn my volts back up to 5 volt per division, and I'll wind the amplitude up until I start seeing it clip. We'll start seeing it clip. Which is about there. It's starting to flat top and flat bottom. So about 1.8 volt peak to peak roughly, and we're pushing out 22.3 volt peak to peak. So I've just remeasured it. We've got about 22.3 volt peak to peak. So we divide that by 2, that's 11.15. Square that, gives us that. Then we divide it by our resistive load, which is not that. We get roughly 15.5 watt. So yeah, it's operating where it should be, between 10 and 15 watt. So that module is also working. Okay, so I've dropped it back down to 1 volt peak to peak input. So now I'm going to go to the sweep function just to have a look at its frequency response. However, I might just increase my voltage per division so I can actually see the waveform. So here we go. 12.67, 12.7, 12.67. It's hovering around 12 volt, not rolling off yet, still at 10 kilohertz, 12.7, 12.5, it starts rolling off at 16. So it is relatively flat from the base frequencies up to around about 16 kilohertz, and then it starts rolling off because we're at 12.7, and now we should see it drop a little. Not by much. So yeah, it is actually functioning, and it has got a nice flat frequency response. Moving on to the next thing, which I have no idea what it is. Okay, I've hooked up a speaker here to it. Hopefully it's not going to blow it up. It shouldn't. I'm just going to do the good old blurt test. Slight pop there. Okay, that's working. That positive lead's not on properly either. It is now. Okay, so next I will do a quick sound test. Sounds alright, but that track's crap. Okay, that's working. So I guess what might be a good idea is if I A, plug my camera into a power supply because the battery's going flat, and B, get rid of the bench supply and hook up that test amp transformer again. Now, yeah, I'm not sure because it's going to draw 1.2 amp roughly per module, so it's probably not a good idea that I hook up both modules to that transformer, just the one. So I'll do the one I've just built to test it. The other one is calibrated and ready to go, but I'm not going to hook up both modules as I just said, because I run the risk of blowing the thermal fuse inside the transformer, because it's going to be drawing 1 amp at idle. The transformer winding's rated at 1.3, I think it is. So anyway, I'll get set up and do that. Okay, it's all connected up to the transformer, so now with a bit of luck it's not going to go off bang. So I'll turn it on. Light came on. Relay engaged, but there was a slight pop through the speaker there when the relay engaged. But that's okay. Can't hear anything coming out the speaker at all. It's dead quiet. So I'm just going to do a quick VCC voltage check on my multimeter. We're actually sitting at 22.6 volts, so that's perfectly fine. Okay, so I now know an 18 volt at 160 VA is going to be fine. I've just got to keep an eye on things because that transformer might start getting hot. If it gets way too hot, I'm turning it off because that'll burn the thermo fuse, rendering that transformer absolutely useless. So now, without further ado, let's hear what that sounds like off its own power supply. About the same. that was alright. The fridge compressor came on and it made a little bit of a click through the speaker, which kind of made me jump just a little. I thought, oh shit, what the hell happened? Nothing. Okay, so that is the 1969 John Linsley-Hood Class A amplifier power supply unit kit. It works very well. Not really happy with the slight pop through the speaker when it's first powered up, and after the 3-second delay it allows the speaker to connect. There's still pop there, which is unusual, but that could have something to do with those 10 ohm resistors that are preloading the amplifier. Just saying. I still haven't quite figured out what its purpose is yet, but it's there for a reason. Anyhow, instant off, not a problem. So I'm just going to let that discharge. Now that it's actually connected to the amplifier, those capacitors will discharge a lot quicker because it's actually discharging through a load, and actually because it draws 1 amp when it's operating, it's going to discharge those caps pretty fast because it is basically 1 amp of current. So I'll see if it will come back on. Yeah, there's a slight pop there, and I'm not sure why it's doing that, but I would say yes, it would have something to do with those resistors. So just to end this video, I will turn the light off so it's not washing out the image. We'll play this classic track yet again because, well, I can.
And there we go. Working perfectly. What am I going to do with these two modules? Now I've got a set, so I've got stereo basically. Well, I don't know yet, but I would assume putting it onto a proper heatsink, putting it in a proper cabinet, and just having it as a standalone power amplifier, which can deliver up to 15 watts, which is enough to fill a room, put it that way. But I'm quite happy with that power supply, apart from the pop through the relay when the contacts engage, as previously discussed. Other than that, it works well, and you can choose to leave those 10 ohm resistors off. I would probably recommend doing so. That would get rid of the click when it engages, I guess, through the speakers. But anyway, I'm going to end this video here, and I thank you for watching, and please remember as always to rate, comment and subscribe below. You can always follow me on Facebook and Twitter, links in the description. There'll be a link to the kit in the description, a link to the power amplifier kit in the description, also a link to PayPal Me, where you can donate as much as you want or as little as you want, because remember, your donation helps me buy shit to test on this channel. And that's it. Thank you for watching. See you next time. And I better turn that off, because now that that's been working, that heatsink is red hot. Just saying. So that heatsink is not sufficient enough for this amplifier module. No way, shape or form. So before I touch that any further, I'm going to have to let that cool down. Anyway, see you again in the next video. Bye for now.